So you're going to miss the first 10 minutes, which was not super exciting anyway. So this condition, of course, applies in all directions. And so overall, what that means is that the vector k, if all the lengths are the same, is 2 pi over L times the vector n. Okay. And what we use that for, we use that so that we can say the sum over n. If there are many, many n's, then this will be roughly equivalent to just integrating over all possible n's. So if there's sufficiently many, we can treat that as continuous. And now I can use this relation between the k's and the n's to convert the integral over n to an integral over k. So d3n will then be L cubed over 2 pi cubed times d3k. Okay. So this is a volume divided by 2 pi cubed times an integral over d3k. Okay. So, so this is the place. I mean, we dealt with this before, where someone said, "Well, now, in principle, I just did it for a box that's exactly a cube, but you can easily check that it also works for a box that's rectangular." And then you can somehow imagine putting many boxes together to convince yourself that it really doesn't have to be a box at all. It could just be any volume. Okay. So just a reminder, by the way, if there's something you would like to, oh, I see, indeed, somebody asked something. Okay. So Clayton, I think you can just step in.
Yeah, so I was just going to ask, what is the advantage of working in K space instead of N space?
Well, roughly speaking, because I diagonalized my Hamiltonian now and I wrote the energy eigenvalue in terms of K. I mean, if you wish, I could have expressed the energy eigenvalues in terms of N and just never switch. But this N is something, you know, is some feature of the system that actually remembers exactly how you discretized it. Whereas the K, in some ways, is closer to just a continuum version of the whole thing. So I think people find it more physical or more intuitive to write everything in terms of K. But for now, it's basically because I wrote the energy eigenvalue in terms of K. So this epsilon was written in terms of K squared over 2m. Could have tried to write it in terms of n, and then I avoid the Ks. Okay. So, so what that means then is that the sum over n has now become a factor of the volume divided by 2 pi cubed. And we have this integral d3k, but since the energy really only depends on the absolute magnitude anyway, we can write that integral in terms of spherical coordinates. So we can write it as k squared dk. The next trick, which is also not absolutely necessary, there's various ways of doing it. But again, since the boson and Fermi distributions are usually written in terms of energy, not in terms of momentum, it's also useful to now switch variables from k to epsilon. So our energy, remember, so our energy was epsilon is h squared k squared over 2m. And so that means d epsilon by dk is h bar squared over m, k over m. And so this means we can change variables, so we can write dk as d epsilon m over h bar squared, and m, there's too many m's here. There's one m too many. This is a 1 over k. Okay. So, so if I change variables like this, my sum over n becomes, it's now volume, so the 4 pi over 2 pi cubed, that's 1 over 2 pi squared. So the k squared dk So 1k goes away, 1k is still here. That's d epsilon m over h bar squared. And now, of course, I can write that k in terms of epsilon. So k is given by, I look at that expression for epsilon, so it's the square root of 2m epsilon over h bar squared. Actually, no square. I take a square root. So I will try, by the way, I think I have a feature where I can save this whiteboard and hopefully post it later, all the pages that you see. But in principle, I'm just following my notes. So you should also be able to just follow along on the notes. Okay. So then I can finally collect everything. So my sum on n is the volume over 2 pi squared. There was a factor of m. We have in total a factor of h bar cubed. There was a root 2m, and then a factor of square root of epsilon d epsilon. So this whole factor in front is volume mass to the 3/2. There's a root 2, there's a pi squared, and an h bar cubed. And then there's this integral square root of epsilon d epsilon. And so I will do two things again that we did before. Number one, this whole expression with the root epsilon, that's usually called the density of states, and I will call that g of epsilon. And this g of epsilon is some kind of constant times the square root of epsilon. Okay. Okie dokie. So where are we? So so we go back to our Bose distribution. So what was our Bose distribution? The Bose distribution was, oops, what am I doing? Okay. So this is the probability that some state with energy epsilon is occupied if you have a given chemical potential and a given temperature. Okay. And you can use that expression to perform all sorts of averages. The simplest average you can perform is just ask yourself, on average, how many particles total as a function of chemical potential and temperature. And so the total number of particles as a function of chemical potential and temperature is just the sum over all possible states of this Bose distribution. So it's the sum over all possible states, NB of epsilon for this particular state. But the sum, we now converted to a continuous integral. So we wrote this continuous integral as an integral over epsilon of g of epsilon. And now I just write down the Bose distribution. So this is E of epsilon minus mu over k Boltzmann T minus 1. So that's the total number of particles as a function of chemical potential and temperature. Now, in practice, of course, it's more typical for us to think not in terms of chemical potential, but in terms of the number of particles as sort of the given variable. That you have a box and you stick a certain amount of material in, you stick 1 mole of helium or something. So then what you would know is not mu, but you would know the number of particles. But in principle, you can always compute this integral and then invert it to give you mu for a given n. So in practice, the way you should think about this is that I specify the number of particles, and then we adjust the mu until we get the right n for a given temperature. Okay. So that's some of the exercise. But now let me remind you of two things. So number one, So for this system to make sense, we needed the mu to be less than 0. And you can also see, just by looking at this integral, that the number of particles will increase with the chemical potential. So the derivative of n with respect to the chemical potential is greater than 0. So if I were to somehow plot this, so I plot the number of particles as a function of the chemical potential, what I get is something that looks something like this. Okay, so some kind of function that increases with mu. Okay, but the allowed mu's stop at 0, because otherwise, again, there's some kind of funny singularity in the distribution function. So you can immediately see what the potential problem with this is, which is that it looks like there's a maximum number of particles that can somehow be accommodated. It somehow becomes mysterious exactly what happens if there's too many particles. So in this plot, by the way, again, way down here, that's the classical limit. Because in a classical gas, if you go back to the expression we had for the chemical potential as a function for the density, so we worked that out a little while ago. So if the gas is very hot, that chemical potential becomes quite negative. It's of the form minus, mu is of the form minus kT times the logarithm of the density, if you go back to that formula. So the classical limit corresponds to a low density. If you make the gas very hot, it's typically at low density, and a chemical potential that's quite negative. And then it becomes more and more quantum as the chemical potential goes closer and closer to 0. So as you see from this plot, the potential issue with this expression is that there appears to be a maximum number of particles. And so you can just find what that number of particles is by setting the chemical potential to 0. So that's the largest it can become. And so we can just see what the number of particles is in that limit. Oops, that's not what I wanted to do. I wanted to make a new. Here we go. Okay. So I can compute. Oops, that was not very nice. I can compute the number of particles for mu equals to 0 at some given temperature T. Okay. So that's d epsilon g of epsilon e to the epsilon over kt minus 1. This, by the way, again, if the chemical potential has the wrong sign, this integral is ill-defined, but for mu equal to 0, the integral is perfectly well-defined, as you'll see in a second. So this integral is of the form, there's some constant in front, and then g of epsilon had a root epsilon in it. Okay. And the way you can see that this integral is actually perfectly well behaved is, so the potential danger in this integral is near epsilon goes to 0, because then this exponential is very close to 1. So in this limit, this exponential is roughly 1 plus epsilon over k Boltzmann t. So if you subtract the minus 1, the denominator is roughly epsilon. So in this limit, the integral is of the form d epsilon root epsilon divided by epsilon, but that's of the form d epsilon divided by root epsilon. So the smallest epsilon is 0, goes up to infinity, and 1 over root epsilon is kind of singular at epsilon goes to 0, but it's not so singular that it can't be integrated. So it's a perfectly finite integral. So the total number of particles is still well behaved at mu equal to 0. It's just that something funny happens if mu becomes positive. So this can actually be computed. And so I do that in my node. So it's an integral that, the way you compute the integral is you change variables. Let me just indicate what we would do here is, so we would introduce a new variable, say x, that's just epsilon over k Boltzmann t. And so then this integral would be of the form, so we have this constant in front. So we have d epsilon root epsilon, so that will be a factor of k Boltzmann t to the 3/2. And then the integral is an integral dx root x e to the x minus 1. And this integral goes from 0 to infinity. And so that turns out to be an integral that if you punch it into Mathematica, it'll just spit out an answer, or you can look it up. So this integral is equal to, I think, root pi over 2 times the zeta function of 3/2, which is just some number, which I cannot recall. Of course, I think the zeta function of 3/2 is something like 2.6 or something like that. Okay. So now I can just write down, and that's somehow written somewhere in my notes, is what is n of 0 now? So n of mu equals to 0 and t is the total volume that was hidden in this factor L cubed. So there's a total volume factor. There's 2 pi m times k Boltzmann t. Actually, let me do one thing. Okay. Let me start here. So it's m k Boltzmann t divided by 2 pi h bar squared to the 3/2 times this zeta function of 3/2. And what is often done is that we use the fact that, I mean, usually it's better to write everything in terms of h bar. This is one of the few places where it's usually written in terms of h. So 2 pi h bar, and that's just Planck's constant itself. And so this one looks a little more transparent if written in terms of h. So this becomes volume 2 pi m k Boltzmann t over h squared to the 3/2 zeta of 3/2. And the reason that that's somehow more transparent is this factor in the square brackets you can now recognize as the de Broglie wavelengths, which again is something we introduced earlier. So this is volume divided by the de Broglie wavelengths to the 3rd power zeta of 3/2. So just de Broglie wavelengths is h over the square root of 2 pi m k Boltzmann t. So that again is roughly speaking the wavelengths of these quantum particles. So if the temperature is very high, that's the classical limit, and the wavelength becomes very short. And if the temperature becomes kind of low, then you're more and more quantum. So this expression, I can write it, so n over v is just the density of the particles. So I can write it as n, which is the density of the particles, is 1 over lambda cubed times zeta of 3/2. Okay, so this n, by the way, again, so that n is the n at mu equals to 0 for some given temperature T. Okay. One way to think about this, by the way, is that this lambda cubed is some kind of volume. And I think I introduced that earlier. Roughly speaking, you can think of it as the sort of quantum volume of a particle. It's the volume that corresponds to kind of the size of the wave function of a single particle. And so if lambda cubed is a kind of quantum volume, then one way to say this is that this density is just some number, which is zeta of 3/2. So that turns out to be roughly 2.6, divided by some kind of quantum volume. So it's 2.6 particles per quantum volume is somehow the largest number of particles that I can put into this system. Okay. Now, again, so the question is, what on earth does that mean? Obviously, you would imagine that nobody prevents you from putting in more particles than that. So you have a kind of box, you fix the temperature, and you start to put in more and more particles. And what that means is that the chemical potential becomes larger and larger, which is less and less negative, until the chemical potential goes to 0. And at that point, you've put in 2.6 particles per quantum volume, but you would imagine that nobody prevents you from putting in more. And so the question is, what happens next? And the main thing to realize is that we have to be careful with this approximation that we made, which is we replaced the sum over all possible states of the system. We replaced that by a continuous integral. And that's generally fine if the states are close enough together. So, you're somewhere up in the spectrum, there's gazillions of states, and most of them are actually empty. But the one place where you have to be careful with that is sort of at the edges, because there is a lowest energy state. And now we somehow treated the whole thing as continuous. So, so the one thing we have to be careful about is that we have this function g of epsilon, which somehow counts how many states there are in some interval epsilon, okay? And in our approximation, we treated that as a perfectly continuous function. So it's some kind of function that's proportional to the square root of epsilon. That's the approximation that we made. But that's, of course, not quite right. The reality is that there actually are individual states. So there's just one ground state, and then, there are many other states. And this g of epsilon, of course, approximates their density, okay? So if you're somehow high up in the spectrum, that should be perfectly good. But the one place where that's potentially dangerous is down here. So down here, that's potentially not right, because our continuous spectral density is exactly 0 at epsilon equal to 0, but there actually is a state there, okay? So somehow the one mistake, or the most important mistake that the continuous approximation makes, is that it ignores the fact that there actually is a state. And for bosons, that's an important difference, because that one state can hold an arbitrary number of particles. For bosons, there's nothing that prevents you from putting in as many particles as you would like. So once you get to that point where you put more than 2.5 particles per quantum volume, then really you have to be careful with replacing the sum by an integral. You should really use the sum. Now, that's kind of tedious to really use the sum. So it turns out to be good enough to just fix that one mistake, the one about the ground state. We just treat the ground state separately, and we approximate all the other states by a continuous integral. So the thing that we can do, and that turns out to be good enough, although you can go home and try to do real sums, is to write the total number of particles as the number of particles in the ground state plus all the others. Okay. And this continuous piece we will approximate by the integral we computed earlier. Okay. Okay. So now we can see what will have to happen if you increase the number of particles beyond the point where you cannot put in any more into this continuous port. Once you try to put in more particles into the continuous port, you just can't do it. And then there's only one place where they can possibly go. So they have to go into the ground state, okay? Before you get to that point, you can compute the probability. You still have you still have a negative chemical potential. You can compute the probability that there is a particle in the ground state. That probability is not 0, but it's never truly macroscopic. So there's, you have 10 to the 23 particles. Even before you get to that point, maybe there's 1, or maybe there's 2, there could even be 3, but it's never of the order of 10 to the 23. But if you get beyond that kind of quantum limit, then everybody else now has to go into the ground state. Now, in practice, by the way this comes about is not by increasing the number of particles. The experiment one does most often is that what you actually do is you fix the number of particles, but you lower the temperature. That has the same effect because the quantum volume becomes bigger as you lower the temperature. So if you have a limiting number of particles, which is 2.6 per quantum volume, and you lower the temperature so that the quantum volume increases, then that will also get you to this boundary. Okay? So there will be a magic number of particles or a magic temperature where you hit that boundary. So again, for that purpose, let me rewrite this expression that we had previously in terms of T. So we had the number of density of particles, okay, that was 2 pi m over h squared to the 3/2. And now explicitly write the factor of the temperature. I don't absorb it into this de Broglie wavelengths times zeta of 3/2. Okay, so for a fixed number of particles, one way to think about the problem is to just solve this equation for the temperature. So if I do that, I get kBT is density to the 2/3, and there will be a factor which is h squared over 2 pi m, and then we get this 1 over zeta to the 3/2, and now we have to take the 2/3 root of that. Okay. So the magic expression is that K Boltzmann T is h bar squared over 2 pi m, and then it's the density divided by zeta of 3/2. Again, that's just a number to the 2/3. So for a fixed density, if you lower the temperature, that's the magic temperature where you hit this kind of quantum bound and you can't put in any more particles. So that temperature has a name. It's called the Einstein temperature. Okay, and what happens? Yeah, so this is now an H bar. So I switched from H bars to H only on that one occasion to get it recognized as a de Broglie wavelength. So now I'm back to H bars, which in general I like better than H's. Okay, and there may be, I can write you an email. So there may be places in my notes where I make mistakes or I lose H bars, but you can always consult your textbook, which hopefully doesn't make that mistake. Okay, but I think this is an H bar in the formula that I just wrote. So if you now think of it, so this is n as a function of t. So if you now think of it as we fix the number of particles, so the total number of particles never changes, but we lower the temperature. So then what has to happen is that, so initially almost no particles are in the ground state, almost all particles are in this continuous part of the spectrum. But then you get to that magic temperature, you get to the Einstein temperature. And at that point, you can no longer put all the particles into this excited state, into the excited state part of the spectrum. You have to start putting particles into the ground state. And how many sit in the excited state, you can just compute by continuing to compute the number of particles. So if you make the temperature lower and lower, the total number of particles in the continuous part of the spectrum, which is now fixed at zero chemical potential, will now start to decrease. So you get something like this if you just continue to compute that integral. And so what that means is the remaining particles now have to go into the ground state. I lost my whiteboard. What did I do with it? Okay, that one's still there. Oh, here it's back. Okay. So these are the particles in the ground state. These are particles in the continuum. Okay. Initially, so the curve up here corresponds to some mu that's less than zero. But since the temperature is getting lower and lower, the chemical potential is rising. This here is the magic point where the chemical potential hits zero. But I can't go any lower than zero. So in the continuous part of the spectrum, this is still mu equals to zero. But because the temperature drops, the number of particles are dropping. And if you go back to that expression, I'll quickly show it to you wherever we had it. Here it is. So you see that the number density of particles goes as temperature to the 3/2 at zero chemical potential. So if you sit at zero chemical potential, you continue to lower the temperature, the number of particles is dropping. And these remaining particles, now they all have to go into the ground state. So that's the picture behind post-condensation. So you have this magic scenario where there is a finite number of particles, all of them in the ground state. So there's a finite and indeed macroscopic. So, if you have 10 to the 23 atoms, they're now on the order of 10 to the 23, and eventually all of them. So there's a finite macroscopic number of particles. In the ground state. And so this means this is some kind of macroscopic quantum state, because you have some enormously large number of particles. All of them occupy exactly the same wave function. So you have a large number of particles that effectively just moves as one, okay? And so that leads to unusual macroscopic effects. So famously, for example, that leads to superfluidity. And I think I put some YouTube videos about superfluidity on the Moodle website. So you can take a look at some of them. And now you might think that if somehow suddenly there's 10 to the 23 particles in some kind of quantum wave function, that that would somehow lead to something totally insane, that it would somehow evaporate, or you wouldn't even be able to see it because it's now all just a quantum wave function. But it's still a piece of matter. The only funny thing that happens is that the particles are now kind of strongly correlated because they sit in the same wave function. So if you take a bucket full of helium, which is, eventually it becomes a liquid, so you have a liquidy substance, it doesn't really look all that different from water. If you cool it below that magic point where it Bose-condenses, it's not that something totally radical happens, that somehow it doesn't look like a fluid anymore. It just still looks like a fluid. It just has all these unusual properties that the particles like to move together. And that, for example, leads to this phenomenon of superfluidity. Or, for example, also leads to an unusual phenomenon that now, if you try to rotate the system, I mean, ordinarily, if you have a bunch of atoms, they can just spin around. That's totally fine. But we know that for a single atom to spin, I mean, number one, it's kind of quantized, so it can only spin in multiples of h bar. And in order to spin, you have to explicitly put it into the corresponding wave function. So it was previously in an S state, and now it's in a P state. And these P state and higher partial wave functions, they vanish at the origin. So in order to make an atom spin, roughly speaking, you have to put it into a wave function that vanishes at the origin. But now you have 10 to the 23 particles all in that wave function that vanishes at the origin. So there actually is a point-like defect in the center of this fluid once you start to spin it, in which there aren't any particles because the wave function vanishes. And so that's called a vortex. So if you want to spin a normal fluid, you can just spin it and nothing special happens. But if you want to spin a quantum fluid that's Bose-condensed, then you have to put all the atoms into a P state. And that means the wave function at the center now has to vanish. And that gives us these point-like defects where the system can only spin by forming a vortex. So there are a number of really rather remarkable properties. And again, there's all kinds of little videos that you can look at. Okay. So are there any more questions about Bose condensation? Okay. So in that case, I would continue with the fermions. Okay. So in the case of the fermions, the system is usually referred to as a Fermi liquid or as a Fermi gas. The names are actually used a little interchangeably. And so for us, I will not really make a distinction. I think for now, I'll call it a Fermi gas. It's really more appropriate to call it a Fermi gas right now because we pretend that they really don't interact at all. Okay. So a Fermi gas for us, number one, it cannot be spinless anymore. So in order for this to be a fermion, it has to be spin a half, spin 3 halves, 5 halves, and so on. So the easiest case would just be a spin a half particle. So that could be an electron, for example, or a quark or something like this. I still want them to have some kind of non-zero mass. I will effectively just use a non-relativistic Schrödinger equation. And so the Hamiltonian for this system is exactly the same as before. So the Hamiltonian is still just h is, minus h bar squared, nabla squared over 2m, okay, same as before. And so this means if I compute, if I take my sum, again, I can put them in a box, I can count the number of states. All of that is exactly the same. So I'm going to get this kind of g of epsilon. And the g of epsilon is exactly the same as before, with one distinction, which is that since this is now a spin a half particle, it has two possible spin states. So every single spin can either point up or it can point down. So just g of epsilon is just twice the g we had for spin zero bosons. Okay. So I will use exactly the same g of epsilon as before, just with the factor in front that's twice bigger. And so I can do the same calculation. I can compute n of mu and t, and that's the same constant we had previously, just with an extra factor of 2. So the thing that's truly different now is, so now we have the +1, so there's no longer any issue with the sign of mu. So I can have the mu be either negative or positive, and that will work just fine. So the main new thing is that mu can have any sign. And it's still true that dn by d mu, if you look at this integral, is a perfectly positive function. So in principle, you can now make the same plot. You can plot the number of particles as a function of the chemical potential. And now the difference is that, again, the classical limit is still out here, but nothing particularly dangerous happens if the chemical potential is 0. So this is classical. And here it becomes quantum. Okay. But nothing bad happens with this curve n as a function of mu. Okay. So for a bunch of fermions, you can indeed either just lower the temperature, lower, nothing really exciting happens, or you can take a fixed box and just put in more and more particles and nothing particularly exciting happens. But it is interesting to see, if you lower the temperature, it's interesting to see what happens to this Fermi distribution function. So for the Fermi liquid or for the Fermi gas, the interesting question is, what exactly does the system look like as T becomes very small? So the interesting case is that T goes to 0. And that's an observation I think we already made previously, which is that if you look at this, Fermi-Dirac distribution function, the +1 automatically ensures that the Fermi distribution function can never become bigger than 1. And again, that's just a reflection of the Pauli principle, that the largest number of particles that we can possibly put in is 1. So let's look at this case that the chemical potential is indeed positive. So what I'm trying to plot here, so this is epsilon. This is the Fermi distribution function. Again, the largest it can get is equal to 1. And I assume that there's some that the chemical potential is positive. So there's one place where epsilon is equal to the positive chemical potential of the system. Okay. So then you can easily plot this function. And again, the limiting behavior is always that it can at most reach 1. I'm not drawing this super well, so it crosses over for in the vicinity when epsilon is on the order of 1. And you can see that just by looking at this function. So again, what is the function? So NF is epsilon minus mu over k Boltzmann T plus 1. So you see that if epsilon is much bigger than mu, you have the e to the something is much bigger than the 1. It becomes very small. That is again the classical limit. So that's the classical limit. Okay. If epsilon is exactly equal to mu, then the distribution is exactly 1/2. So this is where it becomes 1/2. And then if epsilon is less than mu, then the exponential becomes exponentially small, especially if the temperature is very low. And then you're just dominated by the +1. And for the system we have in mind, by the way, the lowest energy is just 0. So in some sense, this regime, now it doesn't really exist anyhow. So really what I should plot is some distribution that looks like this. Okay. And this crossover between 1 and 0, that becomes sharper and sharper if you go to lower and lower temperatures. So at higher temperatures, that will look something like this. So this is at a higher temperature. Okay. And the green curve corresponds to a low temperature. So in the extreme limit, by the way, it's then clear that if you make t very, very small, then epsilon minus mu over this very small t is now either a very large positive number or a very large negative number. So then this e to the something is either 0 or really, really big. So this means you're just crossing over between the Fermi distribution being 1 and the Fermi distribution being 0. So the extreme limit of t goes to 0. So if you go all the way to t goes to 0, then what this distribution will look like is just a sharp distribution like this. Okay. So again, this is the Fermi distribution as a function of epsilon, and this point is epsilon equal to mu. So since the point epsilon equal to mu is kind of important, it's often given a name. So it's usually called the Fermi energy. So epsilon Fermi is simply defined to be the chemical potential. So in this extreme limit, where you take the temperature all the way to 0, the situation you have is that all the states below the Fermi energy, which is equal to the chemical potential, are occupied, and all the states that are above the Fermi energy are unoccupied. Okay. So all of this stuff, there's exactly one particle in any of these states, so these are all filled. Okay. And all the states above the Fermi energy are empty. Now, you might ask yourself, why is it that we need a name for the Fermi energy, given that it's just a chemical potential? Why don't we call it chemical potential? And the reason that that's being done is, strictly speaking, of course, all the systems that we're really interested in are not non-interacting. They have some interactions. And so real electrons in the metal are not non-interacting particles. They interact by the Coulomb interaction, and they have to interact with the ions and so on. And so people have studied the question exactly what happens to this thing when we turn the interactions on. And the short answer is that the distribution still looks exactly like that there's all states below some magic energy are filled, and all the states above some magic energy are empty. But once the system is interacting, that energy does not have to be precisely equal to the chemical potential. So in an interacting system, that can be more complicated. And so that's why we have a kind of separate name for the whole thing. Okay. So let me see, how much time do we have left? We have about 10 minutes. So first of all, a useful calculation, unless there's any questions, no, let's just continue. So a useful calculation you can do is just how many particles are there, as a function of the chemical potential. So that, again, is now a super simple calculation. So I can compute the number of particles as a function of the chemical potential for temperature equal to 0. And so that's 2, that was the spin factor, times just funny constants that always floating around. The density of states was proportional to square root of epsilon, the epsilon, and now all the states below the Fermi energy are filled, and all the states above the Fermi energy are empty. And so the Fermi distribution is effectively now replaced by this step function. It has only 2 possible values because we sit at temperature equal to 0. Okay. And that's, of course, an integral you can do. So you get twice this constant. And the integral of root epsilon is epsilon to the 3/2. So you get epsilon to the 3/2, and so there must be a factor 2/3 in front. Okay. This particular calculation, by the way this is usually done, so this g of epsilon, it came from changing variables from epsilon, from k to epsilon. But if all you do is just count how many particles there are, it's actually even easier to just do this in terms of k. So I can write n of mu comma t. Actually, it's t equal to 0. Okay. So when we started in k space, this was this factor 2 that comes from spin times the volume divided by 2 pi cubed. And it was an integral over d3k. Okay. And so just as there is a largest energy called the Fermi energy, so that all the states below are empty and all the states above, all the states below are filled, all the states above are empty, there's a corresponding momentum now. So that's because energy is just proportional to k squared, there's some kind of magic k, so that all the k's below that are filled and all the k's above it are empty. And this k, of course, is just defined by epsilon Fermi is h bar squared k Fermi squared divided by 2m. So again, epsilon Fermi was just the chemical potential, and this is the relation between wave number and energy. So this just for a given epsilon Fermi, this expression just defines this kf. So this kf has a name, by the way, it's called the Fermi wave vector. And if you remember your quantum mechanics, then you know that h bar k is a momentum. So you can define a Fermi momentum, which is just h bar times k Fermi. So if you have a piece of metal, you make it very cold. Again, then you're in this limit where the Fermi distribution is either 1 or 0. And then what this means is that there's a magic momentum, so that all electron states with an absolute magnitude of the momentum less than that are now filled, and all the states with momenta that are larger than that are now empty. Okay. So let me think. Actually, I think this is a good place to stop. So so I was going to do 2 more things, but we can do that on Wednesday. Number 1 is I was just going to do, actually on the homework, if you wish, I have a bunch of example calculations where I effectively just ask you to look at a bunch of Fermi systems that are either made of atoms, or they're made of electrons, or they're made of protons and neutrons, and just numerically estimate what these numbers actually are. I mean, how cold do you have to make it so that you effectively just get this Fermi distribution? And, you know, is that 1 Kelvin or 1,000 Kelvin or 10 to the minus 3 Kelvin? So it's just an important number for different systems. Where do you get to the point where quantum mechanics is truly important? So I asked you to estimate that for a bunch of systems. And maybe on Wednesday, I can just give you an example for kind of one system, how you, I mean, in principle, it's just plugging in numbers. But since h bar and so on are kind of small numbers, there's sort of efficient ways of doing it. And so that's one little calculation that I was going to do. And the other little thing that's kind of important, which I can maybe already sort of briefly mention, and then we can do it in more detail on Wednesday, is that the thing that's somehow magic about this Fermi distribution, okay, let's go maybe back here, okay? So you have this Fermi distribution. The magic about fermions is that, so in the classical limit, so that's this kind of red curve that we see here. In the classical limit, almost all the distribution, you know, it's effectively just a Boltzmann distribution. So there's some states with high energy that are filled and some states with low energy that are filled. But the filling fraction for any of them is really much less than 1. Okay. Now, you might imagine, so typically as you lower the temperature, of course, you lower the average energy of the system, because fewer and fewer high energy states are occupied. And if you did that completely in the classical limit, as you go to zero temperature, eventually you'd have a system with zero energy, because then indeed it's only extremely low energy states that are occupied, and the average energy of the system would just go to zero. But for a Fermi system, that's not what happens, because I only have one ground state. In the Bose system, I can just put all particles in that one ground state and the energy is zero. But for a Fermi system, I can't do that. I can only put one, or if it's spin a half, I can put two particles in the ground state, but the next two particles have to go into the first excited state. So for fermions, there's always a limit to how low you can make the energy of the system, because you cannot just put all particles into the ground state. Some of them have to go into excited states. And so the total energy of a fermionic system, eventually, it's not dominated by thermal motion. It's just dominated by the fact that they cannot all go into the ground state. So the energy is now purely a counting problem. How much space do I have in states of a certain energy? Okay. So for a Fermi system that's sufficiently cold, the total energy is just dominated by this, what's sometimes called Fermi energy. That, it's the Fermi motion of the particles that gives you a non-zero energy. And as we'll see in a little bit, that's also true for the pressure. So for an ordinary classical gas, the pressure is proportional to the temperature. You make the temperature lower and lower, you eventually end up with zero pressure. But for a system of fermions, that's not the case. Just as the energy cannot go arbitrarily low, the pressure cannot go arbitrarily low, because you always have to put particles into states that have some amount of momentum. And as a result, if you compute the pressure, you get a non-zero answer, even if the temperature is arbitrarily low. And that is actually the dominant source of pressure for many kind of quantum states of matter. So for electrons in a metal, the dominant source of pressure is not thermal motion, it's just Fermi degeneracy pressure. It's the fact that they cannot all be at zero momentum. Or for the neutrons in a neutron star, the source of pressure that prevents the star from just collapsing to a black hole is not thermal motion, it's Fermi degeneracy pressure. And so that's actually a kind of important thing for the stability of ordinary matter, that for anything that's made of fermions, and effectively, essentially everything is made of fermions, because electrons are fermions, neutrons and protons are fermions, quarks are fermions. So ordinary matter is all fermions. And fermions always have a sort of ultimate source of pressure. So fermions, even if you make them quite cold, have some source of pressure that will prevent a piece of stuff from just collapsing. And that's actually the dominant source of pressure for many ordinary materials, that prevents them from just collapsing. So, so the fact that somehow stuff exists and doesn't just collapse onto itself, Fermi pressure is an important ingredient in that. Okay, and so we'll talk about that a little bit more on Wednesday. Okay, so so if you have any questions, you can type them into the chat. You can just unmute yourself and try to ask a question. So if not, I will try to save this recording and try to post it. I'll try to save the whiteboard and also post that. You can always email me questions. You can also let me know how well this works. Like, let me know if I talk too fast and it's hard to follow. Let me know if I somehow write too fast on the whiteboard, your connection is too slow and it's somehow hard to follow. So you should just let me know how well this is working, because it's hard for me to sort of, firsthand see how this is going. Okay, well, thanks for the comment. So I'll try to save this recording, and I'm sure, again, I don't, we sometimes have Zoom meetings, but I don't think I ever really tried to Zoom lecture. So I'm sure we can also fine tune this a little bit in the future. And thank you so much. And I think I'll see most of you. We have this little Zoom meeting about the graduate program with the department head in a little bit. So I see you all guys in a little while. And just generally speaking, I hope that everybody stays safe. And I hope that at least by the fall, this will all be back to normal. So let's hope for that. Okay, good luck, everybody. Thanks a lot.
So for those of us that didn't pick up our midterm yet, is there a way we could see those?
Yes, I could try to do that. I can try to scan them in and make them available. So I'm actually doing this from my office. So at some point we may get evicted from our offices if we figure out that I'm actually sitting here. But I can try to scan stuff in before we get evicted. And in that case, I could make it available to you. I'll try that.
Okay, thank you.
Okie dokie. Thanks a lot.